recording today. And we don't want to be in grade 12. There we go. Okay. We made it through this yesterday. That's fine. Okay. All right. I need that workbook so I can see what we've missed. Okay. We missed. Page 106. Page 106. Now you guys have gotten really good at drawing Bohr models. But it's some, and you can draw them in isolation, but one thing that's nice to notice is that there are patterns in how they form ions. So we know that if you have 3 or fewer valence electrons, will those atoms lose or gain? Michael, do you have your book? We are on page 106. 106. One zero six. 106. 106. Okay, everybody, if you have 3 or fewer valence electrons, will you lose or gain electrons to form an ion? You're going to lose electrons. How about if you have 5 or more valence electrons? They will gain. Okay, and now what we're going to do is we're going to take a look at group 1. Everything in group 1. What do you notice about the electrons in the outer shell? Max? They all have just 1 electron in the outer shell. So group 1 are all going to lose 1 electron. So we're going to take that electron and we're going to cross it out. And those are going to form ions with what type of charge? If you lose 1 electron, that's the same as subtracting -1. Yeah? Do you guys know what you get if you subtract -1? Yeah, Maya. You get +1. Absolutely. So what that means, and this is going to come in really handy in the next 2 units, everything in column 1, when it becomes an ion, has a +1 charge. So that's kind of nice, and you can predict things, right? You can check your work. You can say, oh, it's in column 1. Did I end up with an ion with a +1 charge? I should have. Okay. Whoa, that was scary. All right, so we're going to cross out all those electrons, cross them out, cross them out. And the other thing we're going to write, I have to get used to the new button on my pen being erased. Neutral group 1 atoms all have whoops, that's not supposed to be an N. So neutral group 1 atoms all have blank valence electrons. How many, and what, oh, actually, before we do that, we need to say, what is a valence electron? Yes. It is the valence electrons are electrons in the outer shell. And what's another word for outer shell? Valence shell. So before we got all excited and took away those electrons in group 1, how many valence electrons do group 1 atoms have? They have 1 valence electron. Okay. Let's take a look at group 2. How many electrons are in the valence shell of all group 2 atoms? Anne? Yeah. How many valence electrons are in group 2 atoms? 1, 2. Remember, valence electrons are electrons in the outer shell. So we have 2 valence electrons. So that's beryllium, has 2 valence electrons. So when it becomes an ion, it will lose 2 electrons. Is that true for all group 2 atoms? Let's look at magnesium. Does magnesium have 2 valence electrons? Yeah. How about calcium? Yes. So every time you have a group 2 atom in column number 2, it's going to have 2 valence electrons. And it's going to lose those to become an ion. And so if it loses 2 electrons, tell your partner what charge it becomes. It becomes +2. Absolute. Thank you, Michael. Now you'll notice we're going to skip all the transition metals. Why are we skipping all the transition metals? How well do Bohr models work for the transition metals? They don't. Okay, they just don't. All right, so we're going to skip over all the transition metals. You notice I just chopped them out, and we're skipping all the way over to group 13. Actually, while we're here, what would we call all of the elements that are here right now? Groups 1, 2, and then 13 through 18. What do we call those groups together? Those are our main group elements. So right now we're only looking at the main group elements. Let's look at group 13. How many valence electrons in group 13? 3. 1, 2, 3 valence electrons. So when anything from group 13, oh my gosh, look, 13 has how many? 3. Oh, isn't that pretty? Yes? Group 2 has 2 valence electrons. Group 1 has 1 valence electrons. Group 13, all you have to get rid of is that little 1 at the beginning, and it's got 3 valence electrons. Yeah? And what? Group 14 has 1, 2, 3, 4 valence electrons. Guess how many valence electrons in group 15? 5. Group 15 has 5 valence electrons. Group 16 has 6 valence electrons. We can go through and we can circle them all if you want to. 1, 2, 3, 4, 5, 6. Group 17 has 7. Yeah. Whoops, that doesn't look like a 7. Looks like some crazy Z. 7 valence electrons. And then group 18, once the shell is full, we actually say there are 0 valence electrons. A full shell has 0 valence electrons. And the reason for that is that valence electrons are ones that can be involved in bonding. And bonding happens because they want to fill up their shell, but these guys' shells are already full, so they don't need to bond. So there's no valence electrons. Valence electrons are involved in bonding, and noble gases don't want to bond. Don't worry about knowing that for the test. That's just an explanation as to why it's 0 rather than 8 or 2, okay? All right, so now we know how many valence shells are in each, or sorry, how many valence electrons are in each group. If we look at group 13, we have 3 valence electrons. Are we going to gain or lose electrons? We're going to lose how many? 3 electrons. So everything in group 3, when it forms an ion, it will form ions with a 3+ charge. Elements in group 14 do not tend to form ions. Okay, they just don't. Okay? Instead, they tend to share their electrons, and we'll look more at that in the next unit. So you can just be like, they don't gain or lose. I'm never going to make you draw a carbon ion, because they don't really exist very often. Not that they don't ever, but not very often. Group 15, 1, 2, 3, 4, 5 valence electrons. Yeah, we don't want to lose 5. We want to gain 3. So we're going to put in 1, 2, 3. So they're going to gain 3 electrons. What charge does that give us? -3. Sulfur, 1, 2, 3, 4, 5, 6 valence electrons. It needs to gain 2 to fill up those spaces. 1, 2. So it needs to gain 2 electrons, -2 charge. So we have more patterns here. Group 15 is always going to form 3 minus. Group 16 is always going to form 2 minus. Can you guess what charge group 17 is always going to form? 1 minus. Because they're going to want to lose, or not lose, they're going to want to gain 1 electron. Okay. While we're here, shall we write out the names of the anions? What would we call fluorine? Fluorine, when it becomes an ion, becomes what? Fluoride. Now, I want you to watch fluorine. It's not OU, it is UO. FLUO. FL what? UO. So you have to remember, when you're talking about fluorine, don't get the flu. Or you should get the flu. You will get the flu. I don't know. It's not a good way to remember it, but you should have the flu first. Okay, in fluorine. Oh, whoops, sorry. It's an ion, so it's not fluorine, it's fluoride. Chlorine would become chloride. And you'll notice, what am I putting on these ions? Brackets and a charge. So this is going to become chloride. Sulfur becomes sulfide. Does it matter if I spell it with an F or a PH? Either way is fine. Okay? Either way is fine. And somehow or other, this word sulfur got up here. Just cross that out. I don't know why it's there. Tell your partner what you think oxygen becomes when it becomes an anion. Not oxygenide. Just oxide. Yeah. Oxide. Nitrogen, when it gains those 3 electrons, nitride. It gets pretty squishy down at phosphorus, doesn't it? It's pretty big. Phosphorus becomes phosphide. Is good? Yes.
I was just wondering if this was like on test.
Yep.
I said you write like in -3, like the net dot.
That's fine.
That's fine.
Yeah, if you write 3 minus or -3, I'm not going to get upset either way. Either way is good. And same thing if you've got a negative charge. If you write negative, that means -1. But if you want to write 1 minus or -1, that's also fine. Okay? So do we like these patterns that we're seeing? Does it make it a little easier to remember things sometimes? Okay, good. I think that is it. Now, I got some choices for you today. I have oodles of review material, should you want it. But I thought it might be nice for us to see a couple of demonstrations, perhaps see some elements that are like less common. Would we like to see a demonstration or two? Nobody seems that keen. One person is keen. Anyone else want to see a demonstration or two? Anyone else want to see a demonstration? Yes, I've got 3 people saying yes, so we'll say yes. So we are going to go over to the fume hood, which is here. This thing is the input.
People in front of Valence, that is. That's what I want to. You're going to have a very hard time seeing from where you are. It will be very boring for you if you stay on that side of the road. So we are going to put some water in here. Okay. And the only reason it's on top of that is so that it's higher up so you can see it. We are going to get, excuse me for just a moment here. What I have here is some alkali metals, okay? Now we store them in oil. We store them in oil so that they don't come in contact with the atmosphere, okay? So I will pass this around so you can take a look at it, but just don't open it up. And I think the sodium kind of looks the nicest. How is lithium looking? Oh, lithium looks okay too. So we'll pass around the sodium and lithium. On the outside, you'll notice there's either some white stuff or some black stuff. That white stuff or black stuff is the reaction of the metal with oxygen. So even though it's been stored in oil, it still tends to get a little bit of oxygen in there and it makes a coating on the outside. So what I'm going to do is I'm going to take a larger piece from in here and I'm going to cut it open so you can see what it looks like. It doesn't last very long though. The moment it sees the air, it starts clouding over again, but you'll see it's very nice and shiny. So I'm going to pass the sodium starting over here, okay, and the lithium starting over here. Don't open it, okay? Do not open it. Don't ask stupid questions like that. It makes me anxious. Basically, if you open it, you'll get oil all over yourself. So while we're passing this around, I've got a glass plate here. I'm going to put a bigger piece of the sodium metal. I'm all that waiting from. So I have a bigger piece of the metal. And you know how we always say that metals are hard? This metal is quite soft, and if you're far away, you might want to get closer. Because you're not going to be able to see this. You might want to get closer. Because what we've got here is we've got some sodium metal, and it is soft enough that I can actually. There we go. Look at me go. I can just cut through it like I'm cutting through butter, basically. Yeah. Okay, hang on 1 second, okay? I'm gonna get you to, and you see us really shiny, right? But it's gonna cloud over very soon. So what I'm gonna get you to do is I'm gonna get you to cut this piece in half. You're gonna use this like fork and that like a knife. Right? Yeah, so just hold it. No, you'll see what happens when you get contact with liquid in just a moment. Okay? There we go. Cuts really easily, right? Anyone else want to give it a try? Okay, you can cut this piece in half here. Okay. Right? Okay, we're not on. Oh, good. Don't worry. Don't worry. There we go. Anyone else? I heard me over here. Yeah, for sure. You just cut it in half. Right? Really soft. So alkaline metals are really, really, really soft. Leanne, you want to try? Just cut one of these pieces in half. No. Because otherwise we won't have big pieces left. Yeah? Okay. Just cut it in half. Push. There you go. Okay. All right. Who's next? Okay. Yeah. There we go. Like seriously, it's like really, really soft, right? Like most metals, you think I couldn't do this with iron.
Oh, yeah.
Right? And you want to spread it on your bread? You know you don't. Yeah. If you spread it on the bread and you eat, you stop. Yeah. Okay, are we good? Else want to go? All right. We're going to actually start by using a whole bunch of little pieces. And then if we don't get the reaction that we like, we're going to try a bigger piece. Okay? That's why I went for the little pieces first. Now, do you remember the name of the group to which sodium belongs? The alkali metals. The word alkali means basic. Okay? Now, what the heck is basic? Are you guys familiar with acids? Basic is the opposite of acid. Okay? It means that it will produce hydroxide ions in the solution, which you don't know about yet, but will soon. Okay? So what I'm going to do is I'm just going to slip under here and put away the big piece just for now. Put it in oil. Yeah. This is sodium. It's called paraffin oil, also known as kerosene. Okay? And it's just like a mineral oil. Right? So, no, you wouldn't want to use this one. This is more like you buy this one at Canadian Tire. You can use it for like lamps and stuff. Okay? Yeah. So, what we're going to do, before I put it in the water, I'm going to put 1 drop of a chemical in there that turns pink when it is in base or when it's in alkali solution. Okay? Don't touch anything while I go in there, otherwise you can never do any labs ever again. Clear? Yes.
I think it's not really apple. That is not really good.
Okay. Now, those people who are in front, if you could just kind of like squat down a little bit. Okay. Yeah. I hear you. I feel your pain. Okay, so what we've got here is we've got the metal, okay, and we've got the water, and I put some, it's called phenolphthalein in it, and phenolphthalein is colorless when it's in neutral solution, so that's water, so it's neutral. It's also colorless when it's in acid, but it will turn pink in base. So let's see what happens when we add our metal. And I'm going to turn up the lights so you can see a little better.
Am I in the flat?
On your knee. On your knee. On your knee.
Oh, wait, it's like.
It's got nothing on that story. Wait a minute. Yo. Actually, just kidding. Wait, we don't get it. Wait, we're starting.
Wash off where you have slab.
Oh my god, it wasn't me. I'm not even, I jumped. I feel like I said pop.
That makes sense.
Gunpowder is like potassium nitrate and potassium and nitrogen oxide. Yeah. Why did I keep sure everything is dry before I use it again? Because I don't want it to explode in my hand. I don't want it to explode, right? So it reacts with water. So I'm just making sure that everything is nice and dry before I use it. Okay.
Like 10 in your hand is gone. And one is if you're holding files. Are these the ones we can have seen? If you look at the ones like sparkle, yeah, like
We're gonna do one bigger piece as opposed to many smaller pieces. I'm not actually sure which is better. I thought we got a really good reaction with the smaller ones. I'm not sure we'll get as good reaction with the bigger one, but let's try. Well, this needs to last me until I retire, so. Okay? Are we ready?
Oh, yeah. Oh, very good.
That's a block my way. Do something like.
oh man. That was a good
Now that you've seen that, you guys get to tell me, was that a chemical change or a physical change? How did you know that was a chemical change? We got some bubbles. We got
like a new thing.
we got a new thing. We got some the gas that came off was hydrogen gas from the water. Water is made of H2O, and what happened is that the H2 came out and became the explosive gas that hydrogen is. Okay. It depends. What is that? Is with the sodium it is, and then the sodium is now dissolved in the water in partnership with the OH minus ion. So you know how water was H2O? One of the H's gets together with another H from another water, it forms H2 gas. And then the OH that's left behind is the hydroxide, and that's what turns it pink. That's what makes it into a base. If you were to feel the water, it would feel slippery. Okay, not that we're going to feel the water because that would be not good for you. If you were to taste the water, it would taste bitter. Because bases taste bitter. Are we gonna taste the water?
Yeah.
Oh, because that would be stupid. I'm like the guy who melted the salt and then like had all sorts of other crap in it and then froze the salt again and then it's like, I can drink it. And yes, you'll be sick. Okay, so for starters, phenolphthalein is a laxative. It makes you poop fast and furious. Why do you think those alkali metals are called alkali metals? Do you remember what alkali means? Basic. And what kind of a solution is produced when we put that alkali metal into water? Basic. So we produce an alkali solution. We produce a basic solution, and that's why they're called alkali metals. The alkaline earth metals will also react with water, although not in such a spectacular fashion. They're sort of more gentle, they'll sit there in bubbles. Okay. Bubble. No explosion. Yeah? Yeah. So I'm like, we're not gonna bother with that. We're just doing the fun ones. Okay? So that's it. You can go sit down. Okay.
You know if you put uranium in that thing, the whole school goes wrong.
I don't believe it. Yeah.
Adria, yes. Pardon me? Now, just before we carry on, we are going to just look at a couple other elements because you don't get to see them, okay? Because they're too dangerous to have in the classroom. All right, so I need to go to Science 9, and then I need to go to Labs, and then I need to go to Element Videos. Yes, Rehan?
So I think it's like an obvious question, but it's like uranium one of like the dangerous elements.
It is one of the dangerous elements. You have like this obsession with uranium, don't you?
So like where can you find it?
Gosh.
Wait, does it actually come from the ground or something?
So the last time we tried to film chlorine.
Okay, so we're going to look at this demonstration with some
Chlorine experiments. We found that the chlorine cylinder itself had a slight problem. It was seized here, but the STIG has acquired another cylinder of chlorine. So you know what this means? It means that we feel duty bound to increase the intensity of our chlorine video and show you some chemistry with chlorine.
Chlorine is an element that many people have heard of. It's a greenish yellow gas. and which consists of the gas consists of 2 chlorine atoms bonded together, so it's Cl2, and it's much heavier than air.
Incredibly reactive, incredibly poisonous, not a very nice compound at all. Okay, so Neil is about to open the cylinder of chlorine to allow some chlorine gas to leak through the pipe into the flask in the fume hood. Chlorine sits in the right hand side of the periodic table, the halogens in group, well, some people say 7, some people say 17. Really what that says is that chlorine wants another electron to get that noble gas configuration, and it will move heaven and earth to get that electron.
So during the First World War, it was used as a chemical weapon. The gas could spread across the battlefields, and when it came to the trenches, which were holes in the ground, it would fall into the trenches and fill them up.
You can see the yellow colour against the white background on the paper. So now we're starting to fill that flask with chlorine. It's quite dense, so it will stick to the bottom of the flask. It's not like a light gas like hydrogen or helium. It won't come upwards. So now you can see the colour in that chlorine is really quite intense.
It wasn't a terribly good weapon, because it could quite easily, if the wind changed direction, it could blow the gas back to the people who were letting it out.
So we'll just put a stopper in to contain the gas while we prepare the rest of the experiment.
Chlorine is quite corrosive. It reacts with water to make an acid, HCl, hydrochloric acid, which can attack people's lungs. The lungs generate fluid, they fill up with fluid, and quickly the person drowns in their own fluid. It also corrodes things very easily, so all the metal fittings on people's battle dress, the brass buttons, brass buckles, all went green as well. But it's not a terribly effective weapon, but when people weren't expecting any sort of chemical weapon, it must have been terrifying.
Okay, so we have a small amount of aluminium here, which we put on the end of a wire. We're going to heat the aluminium in that flame, and then we're going to put the hot aluminium into the flask of chlorine. Then hopefully we'll see the chlorine will react with the aluminium, and we'll get very rapid formation of aluminium trichloride, AlCl3.
The British Army created whole regiments of gas soldiers who were all trained chemists who were sent out to handle these cylinders of gas. And on the German side in the First World War, Fritz Haber, the inventor of the Haber process to make ammonia, became very keen on chemical weapons, and he was the chief proponent. His wife was really furious about this, and in fact shot herself with his revolver, killed herself the day before he was due to go back to the front. And it was said that this was because she objected to his work on chemical weapons. Though at the same time, there were rumours that he was having an affair with another woman, so there may have been other factors at play as well.
So, let's heat up our aluminium. Okay, so it's nice and warm all over. And then we'll drop it, we'll add it into the chlorine gas. Now instantly we're seeing aluminium trichloride coming out of the top and reacting with moisture in the air. So now you can see the reaction is getting very intense and we're seeing a flame in the bottom. So the aluminium is being consumed as it's reacting, oxidizing strongly in that chlorine-rich air.
Chlorine is found all over the world. The sea contains sodium chloride, and there are huge deposits of sodium chloride in salt lakes where lakes have dried out, such as in some parts of the States, where you United States, where you have salt lakes where people can race cars and things across the flat surface, and in other parts of the world.
All of the aluminium has been consumed now by the chlorine. Very, very rapid reaction.
There are many areas, such as in the north of England, in the county of Cheshire, and also in Salzburg in Austria, where there are prehistoric deposits of salt from prehistoric salt lakes, which can now be mined really quite easily